This is another example of multivariable integration. We have the double integral over the region where y is between the function x plus 2 and the function 4 minus x squared. So y equals x plus 2 is a line, y equals 4 minus x squared is a parabola. Now in the integrand, it might look like there's nothing there. There's no actual surface that we're integrating and trying to find the volume under, but in this case what we do is we put a 1 there. And so we think of the function as being the function z equals 1. That's a plane that is above the xy plane, one unit away. And then we are going to be on the xy plane with this region here. Parabola opens down, vertex at 4 on the y-axis, and then a line with the y-intercept of 2 and a slope of 1. And so let me show you the wrong way to do it. There's two ways. There's dxdy and dydx. And we'll first do the way that doesn't work so well. With dxdy, you slice horizontally, and then you move it vertically. And so it helps to put the actual slice in there, put the circles at the end, because the circles define the upper and the lower limit on the inside integral. So it looks like it's fine at first, but what you have to imagine is the slicing is moved vertically to accumulate the volume. And so take a second to look at what would happen as if you were to draw another one of these slices. We have this issue of the fact that the upper limit and the lower limit, the ends of this slice, are both on the same curve. And when you have that action happening, that means that you can't perform this integration. Okay, whenever you have the upper limit and lower limit are the same, imagine the integral after integrating, then you plug in the same function, and so it doesn't work out. And so therefore we must switch to the other option, which is dydx. Another drawing, and now we slice vertically and we move it from left to right horizontally. Put the little circles at the end, and this will have the property that the upper limit is the parabola, the lower limit is the line, and it's that way all throughout. Then this will be moved from the intersection, in between the intersection of these two curves. And so we have to find out where they intersect at. I have a nice drawing here where you can maybe sort of eyeball it based off of my axes, but you won't have that, and so you need to be able to know where these curves, these two functions intersect each other. So you have to set them equal to each other. The lower limit will be the smaller of those two intersection points, and the upper limit will be the larger of those two intersection points. And these are outside limits. So we set these two functions equal to each other. X plus 2 equals 4 minus x squared. And then we set this equal to 0. Quadratic, which fortunately is factorable as x plus 2 and x minus 1. Set them both separately equal to 0, and we'll have the fact that x is negative 2 or x is 1. These are our outside bounds. The inside bounds would be the parabola, 4 minus x squared, as the upper limit, and then the line, x plus 2, as the lower limit. And so there's our double integration, set up as dydx, and now we'll perform the integration and be able to get the volume. Think about it as like a cylinder. This is the base, and we have the surface is z equals 1. So think of this as a cylinder with a height of 1. We're finding the volume of a cylinder by doing the area of the base times the height. And so the integration of 1 with respect to y is just going to be y. And then we put the 4 minus x squared in and the x plus 2 in. And now we just have a simple first semester calculus integral. We could simplify by putting together the 4 and the 2 and then rearranging so it's in decreasing order. And then we just integrate this minus x cubed over 3 minus x squared over 2 plus 2x, put a 1 in, put a negative 2 in, and subtract using the fundamental theorem of calculus. When we put a 1 in, we get negative 1/3 minus a half plus a 2. We put a negative 2 in. Be careful here. This is a negative 2 who is cubed, who's already a negative 8, and then it's multiplied by a negative 1. So that's 8/3 positive. And then a negative 1. A negative 2 gets squared here to give you a 4, but then this minus means a negative 4 on top of 2. And that negative 4 on top of 2 is a negative 2. All right, great. So just put these fractions together, and then you'll have the answer. Sometimes it's helpful to put the fractions that have the same denominator together first, because what might end up happening is you might not have an actual fraction at all. We have a negative 1/3 and a negative 8/3. That's negative 9/3. So that's actually a negative 3. And so with that negative 3, together with the other integer values, 2, this other 2 here, and this 4, that'll just give us a grand total of 5, and then we take away the half. 9/2 is the answer.